we're going to start the pre-lab discussion for experiment 5. The objective is to use all the acquired data and result to support or negate the accepted mechanism for this particular reaction, the acid catalyzed the bromination of acetone. This is similar reference you should find in your homework 2, question 2. And in order to determine the mechanism, so when we talk about mechanism of a particular reaction, it usually involves what kind of rate law is there and what's the activation energy barrier, right? So the rate law question is very similar as your homework 1, question 2, and the activation energy barrier is very similar as your homework 1, question 4. So I'll give you 1 moment so you can find your question 2 and question 4 that can help you refresh your memory, and then we'll continue on discussion on this part. Did you guys find homework 1? So the question 2 is method of initial rate, if you remember this one. So in here, you have the initial concentration. You're given the initial rate, reaction rate. And remember, you need to determine the order with respect to each reactant and the rate constant for that reaction. This is going to be very similar as our experiment today. We are going to use different initial concentrations, and we are going to measure the initial rate. So this number will not be given to you. You need to measure this, and the concentration is the concentration you will make for that particular reactant. In the case, which is going to be very similar as this case, so we're going to make one reactant at a constant concentration and change the concentration of the other reactant and then measure different rate. So we can figure out if that reactant is a first order, second order, or zero order. We'll do the same for the second reactant. So we'll make the concentration of the first reactant constant. So here, and change the concentration of the other reactant, and then measure the initial rate and correlate back to the reaction order. Okay, so let's look at the question 4. So in the question 4, you are given the rate constant at different temperature. Remember, in this case, you made a plot using the rate constant and the 1 over the temperature, right? In unit of Kelvin, not Celsius. So once you made that plot, you can use the slope to determine the activation energy barrier for that particular chemical reaction. So we'll do the same for this one, except the rate constant is not given. You need to calculate the rate constant based on the initial rate. Okay. And once you find out the rate constant and the activation energy barrier, you can relate back to the proposed reaction mechanism. Remember, refer to your homework 2, question 2. That one's to ask you to find the literature about the accepted mechanism for that particular reaction. So once you find out, calculate the rate law and the activation barrier, relate back to the literature you find, and compare that with the results in literature. And then you can come to the conclusion whether your results support that mechanism or negate that mechanism. So let's look at a generic reaction. I have AA plus BB, and that will generate BB plus EE. the definition of the rate equal to, so there is a coefficient depending on the coefficient of the equation. So here will be 1 over A, dA dt, and there's a minus sign in front because this is a reactant. So the concentration of the reactant is going to decrease over time, and the dA dt should be a negative number. And in order to keep the rate a positive number, so we put a negative sign in front of every reactant. And for the products, there is a plus sign, so in front of the gradient of the products, okay? So the rate is related to this coefficient times the dA dt, that's the gradient of A concentration over time, and a coefficient times the dB dt, and a coefficient dd dt, or coefficient dE dt. Okay. Also, the rate of reaction is dependent on the concentration of reactants and the products by this reaction. By this equation, the rate equal to a rate constant, the concentration of A to the power of P, and concentration of B to the power of Q, and so on and so forth for the products. The K here is the rate constant. It's temperature dependent. And the P, Q, R, S are the orders of a reactant. And usually they are small integers. So those numbers can run from -1 to 0 or 1 or 2, right? So that's for the generic reaction. If we are looking at the initial step of a reaction, just the initial step of that reaction, because the concentration of D and E is essentially not there. We don't have a D and E yet, so we can reduce the reaction rate to the rate constant times the concentration of A to the power of P, and the concentration of B to the power of Q. Okay, so just notice if the P equal to 0, so if a P equal to 0, that means the reaction is independent from the concentration of reactant A, and then we say the reaction order is 0 with respect to A. Okay. So you will need to calculate P and Q here and approximate P and Q to the nearest integral. The rate law is determined experimentally by either integral or differential method, because we use the initial rate law, and we use the rate definition by the differential of concentration over time. So we use the differential method. For the reaction we discussed today will be acetone. So this one, bromination, catalyzed by hydrogen plus by a proton, and these are the products. So the rate equal to minus acetone concentration over time, and the minus the bromine concentration dt. The catalyst is also participating in this reaction. So the rate equal to the rate constant times the acetone concentration to the power P, and bromine concentration to the power Q, and also the catalyst concentration to the power R. And here, because bromine has color, right? It's brownish color. So this color can be monitored on UV-Vis spectrometer. And if we monitor the color of the solution over time, then we should be able to relate that to the concentration of bromine. Then we can calculate the bromine dt.